Welcome everybody. In what follows, we're going to discuss Chapter 1, Fundamental Concepts. And in this chapter, we're going to discuss some of the fundamental ideas, concepts behind databases, database technology, database management systems, data models, etc. We're going to start with an overview of the chapter. First, we're going to discuss some of the key applications of database technology. Then, we're going to put down some basic definitions. We're going to define databases, DBMSs, database management systems, and a database system. Then we're going to take a step back in time. We're going to look at the file-based approach to data management and contrast that very extensively with the database approach to data management. Then we're going to discuss the elements of a database system. Those elements are a data model, schemes and instances, the tree-scheme architecture. We're going to talk about the crucial role of a data dictionary or a catalog, and we're going to discuss some DBMS languages. We're going to briefly touch upon SQL, which is a very important database language that we're going to discuss very extensively later on. We're going to conclude the chapter by discussing some of the advantages of database design. Applications of database technology. Well, if you look at today's business environment, databases all are over the place. Think about a banking setting, for example. Banks are going to collect information about their customers and every transaction they make. So as soon as a customer makes a payment with the bank, applies for credit, or is going to buy or sell some securities like stocks, all of the information that is related to the transaction will be stored into a database. That could be customer information, like customer name, date of birth, gender, income, marital status, address. It could also be transaction information, like type of credit, amount of credit, duration of the credit, maybe also a measure of creditworthiness of the customer, etc. So all of that information needs to be stored. Also think about a supermarket setting, for example. Supermarkets want to know what products are being purchased by which customers, when they're being purchased, where they're being purchased, and in what quantities. So you see, those are two very popular applications of database technology, and they involve the storage and retrieval of different types of data. The data could be traditional, numeric, and alphanumeric. That means just numbers, letters, characters. But it could also be multimedia data. Imagine that the customer makes a call to your firm and has an inquiry about specific types of products or services, or maybe even files a complaint. Then what happens is that you want to store the audio of the call and connect it to the customer. Maybe you have some videos of your customers that you want to also digitally store. Maybe you have some images of your customers. Maybe you have some fingerprints of your customers. So it need not only be traditional numeric and alphanumeric data, but it could also be any type of multimedia data. A very popular example of a video database application is, of course, YouTube. YouTube stores a tremendous amount of videos. It keeps the videos itself, but also all kinds of information related to the video, like the title of the video, maybe a short abstract or description of the video, maybe some ratings, reviews provided by users, etc. Using database technology, you can also monitor data and autonomously take action when that is required. Think about a stock replenishment system, for example. A stock replenishment system is going to keep track of stock levels, and as soon as the stock level drops below a minimum required value, automatic orders will be placed. All of that can be fully automated using database technology. In a web environment, databases can also be successfully adopted. Databases can be used to store HTML, hypertext markup language information. HTML is a standard which is going to focus on the representation of web documents. Databases can be used to store information into PDF documents. You can have a PDF document that actually has a product description or any kind of product information, and that you also wish to store in your database application. It could also be used to store images, XML-based documents, and so on. In a supermarket setting, you can sometimes have really huge databases. Think about Walmart. Walmart is probably the biggest supermarket in the world. It's an American supermarket. and it's going to store information about all the products that it sells together with all the transactions themselves. Walmart recently decided to also invest into RFID technology, which stands for radio frequency identification. That means that all the Walmart products, instead of barcodes, will be equipped with small antennas. Small antennas that will allow the products to communicate with the database application by means of transceivers built into the roof of the supermarket. That means the database application can continuously monitor where the products are, in what quantities there are, what products tend to pass their expiry date, etc. So this generates a tremendous amount of data, and given the size of it, one typically no longer speaks about databases, but about data warehouses. So data warehouses are typically very large-scale, huge databases with different terabytes or even more of data being collected, sometimes even on a daily basis. Let's look at some definitions now. So a database is a collection of interrelated data. What do we mean with interrelated data? Well, this is data with relationships between the various concepts underlying the data. Think about a university application, for example. So in a university application, you can have different information concepts, like you have an information concept of student, you have a concept of a professor, a course, and a building. Now between those information concepts, you have relationships that exist. A student can take courses, a course can be followed by students. A professor teaches courses, a course is taught by one or more professors. A course takes place in a building. In a building, multiple courses can take place. So you have the data items, the concepts or the objects themselves, student, professor, course, building, and then you have the relationships between them. Well, a database is going to collect both. And it's going to represent some aspects or a subset of the real world, the universe of this course. The universe of this course is the problem setting in which we are working. That could be the university administration, for example. You want to build a system for a university administration. A database is logically coherent. That means all the information items are connected. Students, courses, professors, etc. And it has some inherent meaning. It is meaningful in a particular setting. It also has an intended group of users and applications. So you're going to have different users. You're going to have users like students, which are going to make use of the university administration system just to see what courses they can take or just to register for certain courses, for example. You can have professors that are going to use the university database just to find out what students are subscribed to their courses, how many students, etc. You can have educational program assistants that are going to help students configuring their ISP, individual study program, etc. So you have different types of users and applications. And of course, a database should be appropriately managed. And the way it can be managed is by means of a database management system, or DBMS. And that's a collection of programs, software in other words, that will enable us to create and maintain a database. It will allow us to define, maintain, and monitor a database. So it's like a general purpose software system that is going to facilitate the process of defining databases, but also constructing and manipulating databases. When we say manipulating databases, we mean that it will allow us to insert new information into the database, register new students, for example. It will also allow us to update information into the database, update the marks of a student, for example, or it will also allow us to remove information from the database, for example, removing a course which is no longer offered. So that's a DBMS. It's a collection of software programs that will allow us to do that. A database system is then the combination of both. So it's the combination of the database together with the DBMS, the database management system, software or system. Let's take a step back in time and let's see how approaches towards managing, storing data historically developed. Well, the first approach towards dealing, storing, and managing data is the file-based approach. And that was an approach that was very common in the 60s to 70s of the previous century. Here you can see an example. So imagine we have a couple of departments in a company setting, each with their own application. So we have an invoicing application, we have a CRM application. CRM stands for Customer Relationship Management. It's an application that allows you to manage the customer relationships, understand the needs of the customers, understand interests of the customers, etc. And we have a GIS application. GIS stands for Geographical Information System. A very simple example of a GIS application could be an application that is simply going to figure out where most of your customers live, for example, or where they make their purchases, right? Very, very important information to know. Each of them need data. Of course they do. And the data is being stored into separate files. So you can see 3 separate files here, each storing the data needed for that one particular application. Very important to note is that those files are clearly not integrated. They're separate. And if you have a closer look at some of these files, you see a lot of replication. So you see customer number being recorded here, here, here. Similar to customer name. Of course, each of these files also contains specific information for the application. So here you're going to have VAT code, you're going to have turnover, and zip code, for example. But what is really worrying is the replication or the duplicate data, because that could create all kinds of issues. Duplicate data can very easily lead up to inconsistencies. Imagine that you would change the customer number here. Imagine that your customer base grows substantially and that you want to change the customer number such that it has more digits now because you have more customers. That would mean, in order to make the connection to the other files, that you would have to change it here, you would have to change it there, and then also change the definitions in each of the applications. So it's going to involve a lot of changes that may easily be forgotten, and if they are forgotten, they have very dramatic impact because it means you have bad data of bad quality, which is no longer well integrated. So you see, this file-based approach to data management has a lot of disadvantages that come with it. It has a lot of problems. Let's zoom into some of the problems into a little bit more detail. Well, the first problem relates to accessing the data. If you want to access specific data elements, that means querying your database or your data, then in a file-based approach, you have to manually program your queries. Here you can see a query, find person, which is going to take the name of a customer as input. And basically, you have to program a small do loop, which is going to actually iterate through each of the lines of the file, just to find that one particular person that you're looking for. This is in the file-based approach. So if you have a query, if you want to find particular information, then you have to program it. And of course, it becomes a lot more difficult if you would need information which is stored in different files, because then in your program, you would have to store or you would have to access those different files, bring the data into some kind of staging area, aggregate it, and then make sure that you report the result of the query as desired. So it becomes a very cumbersome exercise to query multiple files simultaneously. This is totally opposed to the database approach. In the database approach, everything will be stored in a database, and the DBMS will foresee DBMS languages to query, manipulate the database. And one of these languages is SQL. SQL stands for Structured Query Language, and just analyze the abbreviation. It's a query language which is structured, so it has certain kind of built-in structure that allows you to formulate your queries in a very user-friendly and effective way. Here you can see an example of a query. Select from the people database where the name is, the particular input name you're looking for. This is a very transparent, efficient way of working with databases. It basically only declares what you need. You no longer have to manually program your query, which was the case in the file-based approach, but you just declare what you want. SQL, as such, is declarative. You declare what you want, and the system will work it out for you, which is really nice, which is really very user-friendly. The file-based approach contains a lot of storage waste, lots of wasted storage space because of duplicates, redundant data. So you have customer number, customer name, remember the previous example, which is being stored in different places. So if you're going to have lots of customers, that will involve lots of duplication of customer numbers and customer names, which is not very nice. So also, if you're going to change your customer data in one file, you will need to change it in all the other files, and you will also need to change the definitions in each of the programs, which is again not very nice. We also have a very strong dependency between applications and data. As I said, the change in the data definition necessitates changes in all applications that use the data. Also, integration becomes very important, so very difficult actually if you want, because in a file-based approach, the information is spread out across different files. So remember the example I gave earlier, in which you want to find information which is contained in those different files. Then you have to access all those files, bring it all together, consolidate the data based upon customer number, etc. So it becomes a very tedious exercise to work out. So it's going to come with really high difficulty, high cost, and maybe the results will not be that very accurate. Let's now contrast the database approach to data management with the file-based approach to data management. In the database approach, the DBMS is going to contain both the data and a description of the database structure and constraints. Database structure and constraints, what do we mean with that? With that we mean metadata. Remember the university application I discussed earlier. So there we had all kinds of information elements, students, professors, courses, buildings. Well, with metadata, we mean data about data. So we're going to clearly define what kind of information we want to store about professors. We want to store professor number, professor name, professor gender, date of birth, etc. Likewise for student, likewise for course, likewise for building. We also want to define the relationships between all those data elements. A student can follow courses, a course can be followed by students. A professor can teach courses, a course is taught by professors. So these are examples of database structure and constraints that should all be stored as metadata in the catalog. The catalog is the heart of the database application, since it contains all this metadata. It contains the data definitions and the data descriptions. We don't have a catalog in a file-based approach. In a file-based approach, only the data is stored in a file, and the structure of the data definitions, are being stored in the applications that will access the file. So that means that you have a lot of duplication of data on the one hand, but a lot of duplication of data definitions on the other hand as well. In the database approach, if you change some of these data definitions, if you change the structure of the DBMS, it only requires updating the information into the catalog. So we can directly update data definitions in the catalog. We don't need to update the applications in any way. So we have program data independence. We have a very loosely coupled architecture there between the programs and the data, which is very sophisticated and which is very nice. This is as opposed to the file-based approach of data management. In the file-based approach, we have not loosely coupled architecture, but a tightly coupled architecture. Programs and data are very dependent. One program is going to access one particular data file, so we have a situation in which changing the structure of a file would require changing every application that is going to access it. In a database approach, we can also have different views over a subset of the data, right? So imagine, again, the university application. So in the university application, we can have, for example, professors, which are only interested in a subset of the information. We can have students which are only interested in course information, for example. We can have educational program assistants which are only interested in certain piece of information. So using views, we can actually select the subset of information of particular interest to a particular user, to a particular application, and offer it to them as such. So a view is basically a subset of your database tailored towards the needs or the activities of a particular set of users or applications. The nice thing about DBMS approach or the database approach is that those views can be defined, stored in the catalog, and then subsequently used. We don't have that in the file-based approach. In the file-based approach, if you would like to define views, it would require copying files, it would require copying parts of files, and any changes made to those duplicates should be carefully merged in all the other duplicates. Databases are also more and more used in a distributed environment. Databases will typically become more and more accessible in a World Wide Web environment on the internet. That means that we should have facilities for concurrent access. Right? Multiple users should be capable of simultaneously accessing the data in the database. Well, for this, DBMSs will include facilities for concurrency control to ensure that No conflicting operations are executed. Imagine that you have a database application in which you have a bottle of wine. You only have one particular bottle of wine, you put it on eBay, so multiple users can actually simultaneously access the bottle of wine, but as soon as one user makes the purchase, the bottle of wine is no longer available to the other user. So you have to make sure that only one user can make the purchase and not two people purchase that one bottle of wine, because that's simply not possible. So in order to achieve that successfully, the DBMS needs to have facilities for concurrency control. In a file-based approach, this becomes a lot more complicated. In the file-based approach, it is nearly impossible to have people or applications working on the same file. Those facilities for concurrency control are not available. So, in a nutshell, DBMSs have catalogs. This is not available in a file-based approach. DBMSs or databases have program data independence. In a file-based approach, you have program data dependence. In a database approach, you can have the idea of views, which you do not have in the file-based approach. In a database approach, you have facilities for concurrency control, which you do not have in the file-based approach. Here you can see the DBMS or the database approach to data management again visualized with our previous example. So we have an invoicing application, we have a CRM application, customer relationship management application, we have a GIS application. All of them are going to work by means of the DBMS software, DBMS software, which is going to include both raw data and a catalog. Remember, the catalog contains all the metadata. So it contains all the data about the data descriptions, the constraints, and so on. And the catalog is one of the key differences between a database approach to data management and a file-based approach to data management. In what follows, we're going to zoom into some of the elements of a database system. First, we're going to talk about data models. Then we're going to talk about schemes and instances. We're going to extensively outline the tree scheme architecture. We're going to talk about data dictionaries. A data dictionary, also referred to as a catalog. So data dictionary and catalog are synonyms. And then we're going to discuss about DBMS languages. Data models are very important in this course. Basically, in subsequent chapters, we're going to discuss different types of data models. And what's a data model? A data model is a collection of concepts that can be used to describe the structure of a database, the data types, relationships, and constraints. Let's illustrate this with an example, again with the university application. So there we have the different types of concepts. So we have a student concept, we have a professor concept, we have a course concept, we have a building concept. And we're going to discuss those concepts and model what kind of information we want to gather about each of those concepts. So for a student, we want to gather student number, we want to gather student name, student address, student gender, etc. For course, we want to gather course number, course name, study points, etc. We're also going to discuss the data types. The data types are how the information should be represented. Student number is an integer. Student name is a string. Student email address also has a particular data type. So it's just like a set of characters followed by an @ sign, followed by a set of characters, followed by a dot, and then ending in com.be, whatever. You also have relationships which you're going to capture in your data model. So students can take courses. Courses can be followed by students. Professors can teach courses. Courses can be taught by professors. And you also have constraints. A professor should teach at least one course. It's a constraint. A course should be taught by at least one professor. That's a constraint. A student should take at least 60 study points or courses during an academic year. That's a constraint. So all those information elements, together with the data types, the relationships, and the constraints, should be appropriately captured in the data model. Data modeling will be a key activity in this course. And a data model is typically something which is being made between a business analyst or a business user, I would say, let's call it the business user, and a data modeler. The business user is the person that is going to use the database application and that understands the business problem. The data modeler is the person which is going to make the data model, and he or she wants to understand the business problem to make sure that the data model is as accurately as possible a reflection of the underlying business problem. You want to capture the information needs as accurately as possible. And there exist different types of data models. The first type of data model is a conceptual data model. Conceptual data model is a high-level model. High-level, that means it's very user-friendly. It is not very specifically oriented towards implementation. So it contains high-level concepts. It has a representation of part of the reality, and it's close to how the user perceives the data. Types of data models, well, we have the EER model. That stands for Enhanced Entity Relationship Model. We're going to extensively comment on that in due course. And object-oriented models. These are two examples of conceptual data models that we're going to come back to. Next to that, you also have data models which are going to be more implementation focused. Here we're going to discuss concepts that may be understood by end users but are not too far removed from the physical data organization. So we're getting closer and closer to the implementation here. They're going to hide some details of data storage but can be implemented on a computer system in a direct way. So those models are technically a little bit more detailed than the conceptual data models, which are more high level. Examples of implementation data models are the hierarchical model, the network model, the relational model, and the ODMG model, which we're again going to come back to later on. The physical data model is then really the lowest you can go in terms of implementation, because here we're going to have a low-level model that is going to describe the concepts and the data's physical storage details. Here we're really going to describe how the data should be physically organized. And the way you're going to do data modeling typically is that you're going to start from a conceptual data model, very high level, and you're going to make it more and more implementation specific. You're going to make it more and more specific to the physical environment until you end up with a physical data model. Also very important is the concept of schemes, instances, and a database state. In every database application, it is very important to distinguish between the description of the data, the metadata, the data definitions, the data structures, constraints, etc., and the data itself. A database scheme is a description of the database. So it's basically the metadata. It describes the data structures, the connections between them, and so on. And typically, this is specified during database design and is not expected to change too frequently. So here, we're again talking about those data definitions like professor, students, course, building, the relationships between them, and all the data items that we want to capture about them, student number, name, etc. All of that needs to be specified during database design, typically in collaboration between the business user and the data modeler. And once both of them have agreed upon those definitions, we will store them in the catalog. Remember, the catalog is a very essential part of the database approach towards data management. So this is the database scheme. The database state is then the data in the database at a particular moment, which is also called the current set of instances, the current set of observations. It's the data currently in the database. So let's just illustrate that. Here you can see a database scheme. You can see some data definitions. So we have a student information concept, which has number, name, address, email, course, number, name, and building number and address. Now, this is something which is going to be static. That means that it's not going to change too frequently. It may change. For example, at some point, you also want to include the student's Facebook account or student's Twitter account or LinkedIn account in the database, but those changes will not occur quite often, every now and then. Here you can see the database state. The database state means the status of the database at a particular moment in time. So you can see a student table with particular students in there. You can see a course table with particular courses in there. You can see a building table with all the buildings in there. This is going to be a lot more volatile in terms of content. So when a new student gets registered, you need to add them to the student table. When a student is going to change address, you need to change it in the student table. When a course gets removed, since it's no longer offered, you need to remove it from the course table. So you see, this is going to contain information that is a lot more volatile. A lot more volatile when compared to the database scheme. The database scheme, data definitions, are typically considered to be very static, whereas a database state, is going to be very volatile. A very important architecture underlying any database application is the tree scheme architecture. Here you can see the tree scheme architecture visualized. We're going to start at the middle. The middle is the conceptual scheme. This is going to involve all the concepts about which we want to gather information. So here you have those concepts like student, you have the concepts like professor, building, and course. And there you're going to model all these concepts. You're going to say what information we want to gather about students, what information we want to gather about courses, what information we want to gather about buildings, and what are the relationships between them. Okay? That's a conceptual model. Now that model needs to be physically implemented at some point. At some point you want to have an internal scheme. Internal means a physical scheme which is going to discuss the physical implementation of that model. So some information may be stored in files, some information may be stored on disk or in the cloud. So you have different ways of physically storing the information. And basically what you want is you want to have physical data independence here. That means both layers, the conceptual layer and the physical layer, should be as independent as possible, such that if you make a change to the physical layer, it should have no impact on the conceptual layer. The external layer gives us the views. Now, what is a view again? Well, a view is a subset of the information in the conceptual level, tailored towards the needs of a particular set of users and or applications. You can have one view which offers you information tailored towards the needs of professors. Another view which is going to offer you information tailored towards the needs of students, and another view which is going to offer information tailored towards the needs of educational program assistants, for example. Now again, you want independence between the external layer and the conceptual layer. So three-level architecture should be built in such a way that you have as much as possible independence between the layers. Imagine that you would do a change at the physical layer here. That means you would physically reorganize your data. Then the above layers should not be affected. If you change here at the conceptual layer, if you add another type of concept about which you want to store information, then your applications, which are going to make use of the views to access the data, should remain unaffected. So this is a very flexible architecture which is going to give us very performing applications. Let's have a closer look here. The external view, or the user views, are situated, of course, at the external layer, and an external view or scheme is going to describe the part of the database that a particular user group is interested in. Particular user group, professors, students, educational program assistant. And it's going to hide the rest of the database from that user group. So by means of a view, you can kind of shield information from particular user groups. Students should not have access to professor information. They should not have access to a professor's salary, for example. So you want to make sure that that information is shielded from students. Professors should maybe not have access to certain type of personal information about students, like medical information that might be stored. Okay? So that can be nicely implemented by means of the views. Views will allow you to actually offer information to specific groups of users and hide from that particular group of users information that is of no relevance to them. So those views can be typically described using a high-level data model or an implementation data model. And we're going to give some examples of how you can create views in what follows. Conceptual scheme is going to specify objects, students, professors, courses, buildings, characteristics of objects, student number, student name, relationships between objects. A student can take courses, a course can be followed by students. Integrity rules, like a professor should teach at least one course, a course should be taught by at least one professor, a student should take at least 60 study points of courses, and object behavior. Object behavior are small pieces of functionality that will allow you to do small calculations, for example. Maybe you want to calculate the average marks that students obtain for a particular course. Well, that's an example of object behavior. Okay? So the purpose of the conceptual scheme is that it's going to hide the details of the physical storage structures, and it's going to concentrate on describing all the information entities, the data types, the relationships, and constraints. And to that end, we can again use a high-level data model or an implementation data model. Internal scheme is then the physical scheme. It means it's a physical organization, so it's going to specify how the data are physically stored, how we can optimally access them using indexes, access paths, etc. A key advantage of using that three-level architecture is independence. So we want to make sure that changes in one layer should only have minimal impact on all the other layers. So if we make changes in the physical layer, we want to make sure it has almost no impact on the conceptual or external layer. If we make changes at the conceptual layer, it should have no impact on the external or view layer. So that's what you want to actually aim for. Here you can see that again visualized in a particular company setting. So imagine that you have some departments that need certain types of information. They need product information, customer information, invoice information, delivery information. And imagine that for products that we're going to store name, description, and cost. For customers, we're going to store name, phone, and address. We store certain types of information for invoices and delivery. So what information that we're going to store for each of those items is specified at the conceptual level, together with the relationships between all those concepts. How it is physically stored will be specified in the internal or physical scheme. So here you can see that certain information is stored in London, in Washington, and Moscow to make sure that from an international perspective, a worldwide perspective, we can have fast access to the data. Here at the external view level, you're going to see the information as it is being offered to some of the departments and tailored towards the needs of some of the departments. So we're going to have some information that is tailored towards the needs of the finance department. That particularly relates to invoicing information where we need product, amount, price, and date. We're also going to have some information that is tailored towards the need of the customer service department. Customer service department wants information on customers like address, phone number, ordered product, delivery address, and so on. And then we have the logistics department, which will need information particularly pertaining to delivery, date, address, product, and amount. So you can see this is nicely implemented by means of the views. The views are actually, as I said before a couple of times already, the views are actually going to tailor the information towards the needs of the particular department, towards the needs of the particular set of business users. The data dictionary or catalog, those are two synonyms of one another, is the heart of the database system. The heart of the database system, since it contains all the metadata. It's going to contain all the data definitions, the data types, the data structures, the constraints, and so on. So it's going to contain actually the definitions of that three-layer architecture. It's going to contain the definitions of the conceptual scheme, which was the scheme in the middle. Remember, the external view or user views, which was the scheme above, and it's also going to contain the definitions of the physical scheme. In order to appropriately implement this, we will need DBMS languages. Languages that will allow us to define all these concepts, that will allow us to define all these constraints, and that will of course also allow us to define those three levels. And DBMS languages can be categorized into two types. First of all, we have a data definition language, or DDL. This is the language used by a database administrator, or DBA. The DBA is the guy which is going to actually work with the database, which is going to set up the database, monitor, and maintain the database. So by using DDL, the DBA can define the database conceptual, internal, and external schemes. So it's a set of language instructions that will allow us to do that and store the results of these instructions in the catalog. DBMS languages also involve data manipulation languages because obviously we do not only want to define the data structures, but we also want to manipulate them. So here we have the language used to retrieve, query, insert, delete, and modify the data. And those DBML statements can be entered either interactively from a terminal, from a computer. You just enter your DML statements interactively, like you do in Microsoft Access, where you can formulate SQL queries, for those of you who are familiar with that, or in a general purpose programming language. In a general purpose programming language, like Java, you can directly embed DML statements in the language. DML statements, which are then going to set up a connection to a database, which are going to query information in the database, update, delete, or insert information in the database. The most popular example of a DBMS language is SQL. SQL stands for Structured Query Language, and it has both DDL and DML instructions. You can use it both interactively, interactive SQL, or embedded in a program environment, embedded SQL. In one of the later chapters of this class, we're going to extensively comment on SQL, and we're going to go through the whole SQL syntax. We're going to discuss how you can define data elements, how you can define queries, how you can work with queries, etc. So these are languages which will be used a lot by database designers, definitely also by database administrators, also by programmers that want to work with databases, but also by end users. End users are people that actually are going to use the database application, and it's very important that they know SQL because that will allow them to formulate queries which are tailored towards their needs. So if an end user wants a particular piece of information, you can formulate it as an SQL query and ask that information then from the database. Okay, so now we have discussed the elements of a database system. Now we're going to look into some of the advantages of using database design. You can see the advantages listed here. First of all, there's data and functional independence, which is a very important advantage when working in a database environment. Then we have database modeling, managing data redundancy, specifying integrity rules, facilities for data security, backup and recovery facilities, and performance utilities. First of all, data independence. This is really a very important advantage of working with a database approach to data management. Basically what it says is that software applications should not be changed when changes occur to data definitions. And when I say changes occur to data definitions, those changes can occur at two different levels. They can occur at the physical level. Imagine that at the level of the physical database model that you're making some changes there. You're changing the physical organization of your data. You're actually storing information instead of in Brussels, you decide to store information in Brussels and New York because that may speed up your applications. That's a physical data change, but it could also involve the definition of a new access path, a way of accessing the data. It could also involve the definition of a new index. An index is like a fast way to find information. It could also involve different kinds of storage media. Maybe at some point you decide to store information in the cloud, for example. Well, actually, physical data independence means that if you make those changes at the physical level, your applications will remain unaffected. They will keep on running. And if you're lucky, they will run faster. So by adopting physical changes, you can have physical data independence. Your applications will keep on running, and they might even run faster. And in order to achieve that, the DBMS is going to provide interfaces between the conceptual and the physical model. Logical data independence is another type of data independence, which means that software applications must not be changed when changes occur in the conceptual scheme. So when we make changes to the conceptual scheme, the concepts, those changes can be made and the software applications will keep on running. Imagine that at some point you want to gather more information about your students. You want to add one piece of information to the student concept, like social media account, Facebook page, Twitter account, or LinkedIn account. Well, you can add that change to the conceptual model, and your software applications, which are going to make use of student information, they will keep on running. So they will not be affected. That's the idea of logical data independence. So whether you add new objects or whether you add new characteristics to objects, Facebook or social media account to students, for example, if you do that in a conceptual scheme, it will have no impact on the software applications because basically the conceptual scheme is hidden from those software applications by means of the views. So the views are going to offer the information tailored towards the application such that changes in the conceptual scheme will not affect any of the applications. To that end, the DBMS will provide interfaces between the conceptual scheme and those external views. Another very nice property is functional independence. And nowadays, if you look at many database applications, databases are going to store more and more small pieces of functionality, small procedures. This is especially the case in object relational databases and object-oriented databases, which will also be discussed in this class. Now, what is a function? A function basically has two parts. It has an interface or signature, which is the name of the function, together with its input parameters, its input arguments that are needed to perform or calculate the function. A function also has an implementation or method, and the method is basically going to specify how the function should be executed. Let's give an example of a function. Here you can see a function calculate salary, for example. So you can see calculate salary. It has certain, this is the name of the function, the interface as we call it, and it has certain parameters like the ID of the employee for which you want to calculate the salary, maybe the wage scale and the time. So you're going to calculate that function, and once you calculate that function or once you execute the function, the implementation or the method here will be executed. So a function has two parts. It has an interface or signature, which is the name of the function and its arguments, and it also has an implementation or a method, which is going to specify how the function should be executed. If your database approach allows for functions, then you have functional independence, because functional independence means that the method or the implementation can change without impact on the software applications. That is the idea of information hiding. What it means is that the method is hidden from the applications. So the applications have no access to the way the salary is being calculated, which is a very nice thing, because that means that if due to changes in the legal environment, tax regulations, social security regulations, if the way a salary is calculated should change, the only place where you should make that change is in the database. And since all the applications work with that function just by calling its name by means of the interface, then you're done. So you only have to make the change in one place. So instead of having to make it in each of the applications which are going to use that function, you only make it in one place and you're done. So that's the idea of functional independence. It's basically something which also stems from OO, object orientation, or this is often called information hiding. That means that the internal representation of objects is hidden from the outside world, such that you can change the internal representation of the objects without affecting the outside world. Another example is sorting. Here you can see two types of sorting, right? The algorithms themselves, the procedures, as you see here, are really not important, and I'm not going to bother explaining them. But for those of you who have a computer science background, you may remember that there exist various ways to sort data. There's like a bubble sort algorithm, there's an insertion sort, there exist other ways of sorting. So if you want to sort information in your database, imagine that you want to sort all your students based upon the marks that they achieved for your course. Then you can either apply a bubble sort or an insertion sort. Both sorts can be implemented by the database without the applications even knowing. The applications are just going to interact with the database and ask, sort the data, and then the database will implement any of those. So basically, you can see a statement here at the bottom of my slide which says, I don't care how it's done, just get it done. So the database can implement it internally itself in various ways. Another advantage of working with a database approach is that you're going to do database modeling. You're actually going to carefully think about the problem area for which you want to build a data model. You're going to come up with a data model. That's already very important. So in a university administration setting, your data model is going to specify objects, characteristics of objects, relationships between objects, integrity rules, and functions. And all of that will be carefully considered. So you're going to have a process which is going to start between the business user, remember, and the data modeler in order to come up with a data model. And that data model should provide a formal and perfect mapping of the real world. When we say the real world, we actually mean the universe of discourse. We mean the problem area in which you're working. And that problem area in which you're working, that could just be a university administration system. So you want to have a formal and perfect mapping. You want to understand all the requirements for that one particular university administration system. And the mappings should be as perfect as possible. They will never be perfect, right? So you will try to approximate reality as much as possible. And where you cannot perfectly approximate reality, it is very important that this is documented. So the limitations of your data model should also be appropriately documented. We're going to extensively comment on that in some of the later chapters, where we're going to talk extensively on data models, discuss the limitations of data models, and how to document them. So in later models, in later chapters, we're going to talk about the hierarchical model, the Kurosu model, the EER model, the relational model, and object-oriented models. We're also going to do exercises in them and make sure we understand the limitations of each of those models. But the important thing here in this introductory chapter is to note that by using the database approach to data management, that we actually start thinking about database modeling, data modeling, and that we're going to come up with a data model which is going to serve as a communication instrument between business user, data modeler, and also the actual implementation. When we discussed the file-based approach to data management, I told you that data redundancy is a bad thing, right? In the file-based approach, we had information that was being replicated, duplicated in various files. And I told you that it was a bad thing, because if you have data replication, data duplication, it can lead up to redundancies which will easily lead up to inconsistencies. That means that you're going to adjust the data in one particular source, but you do not adjust it elsewhere. Now, sometimes you may want to have redundant data. Why? Well, for performance reasons. As I said before, imagine that your databases become accessible in a distributed environment, the World Wide Web, for example. Then you want to make sure that information is available as quickly as possible. And for that, redundancy may be handy, because it will allow you to increase performance by working in a distributed environment and by making sure that you have information accessible to your customers as quickly as possible. Now, the nice thing is that in a database approach towards data management, the DBMS is going to manage redundancy. It's going to have facilities for synchronization and consistency. That means if data is being replicated, duplicated, and let's say a change is made in one of those sources, then the DBMS will make sure that the change is propagated towards the other sources as well. It will manage this. It will manage this data redundancy and replication. So compared to the file-based approach, the DBMS is going to guarantee correctness, and it will do that autonomously. It has built-in facilities to do that. There will be no user intervention needed. In the file-based approach, the user had to actually make sure that those updates, if you make an update in one file, that the update is also propagated to the other files. Well, in the DBMS approach, this is no longer the case. The DBMS will autonomously do that for you. It will take care of that synchronization, and it will make sure that the data is consistent. So this is a lot more efficient compared to the file-based approach. And errors are extremely unlikely. We are not going to say that they're completely unlikely, but they are extremely unlikely because DBMS is going to take care of everything in a transparent way. Integrity rules. Integrity rules can also be specified in a database approach. And integrity rules are going to determine the correctness of data. Here we have syntactical errors, like a customer ID should be numeric. Customer ID should be numeric. That's a syntactical rule which will be specified in the catalog, such that if a customer enters a non-numeric customer ID, your database will give an error. So syntactical rules are going to determine the syntax of the information. Customer ID or customer email address, for example. You can also specify the syntax of customer email address. You can say customer email address has a set of characters followed by an @ sign, followed by another set of characters, followed by a dot, ending in com, ending in .be or whatever. So syntactical errors are going to specify the information syntax-wise. Semantical errors are actually going to provide a little bit more information, like customer IDs should be unique. Every customer should have a unique ID. Or you cannot delete a customer who has pending invoices. Or a student cannot pass if they have failed on certain courses. A student cannot pass or cannot obtain their master's degree if they have failed their master project. Those are semantical rules, and by using the DBMS approach, you will make sure that all semantical rules are nicely enforced, or semantical and syntactical rules. These are integrity rules, and those integrity rules in a DBMS approach are typically modeled up front, again in collaboration between the business user and the data analyst. and then they are nicely stored in a catalog. So the catalog will also contain all those integrity rules, all those constraints. There are in the file-based approach, they will be embedded in the applications, which is not very nice because you're going to have lots of duplication and replication of those integrity rules, which is clearly inferior. That means if you want to change an integrity rule or a constraint, you need to change it in all the applications where it has been embedded, which is from a maintenance perspective, again, very suboptimal. In the database approach, as I just said, those integrity rules will be stored in a transparent way in the catalog, and every time a data manipulation is being made, those integrity rules will be verified and checked to make sure that the update, the insert, the delete can actually successfully take place. So in the database approach, as I said, integrity rules are enforced by the applications themselves. In the file-based approach, I mean, the integrity rules are enforced by the applications themselves. In the database approach, they will be enforced by the DBMS whenever anything is updated. Integrity rules can also be sensitive to simultaneous usage of data in a distributed environment. Remember the example I gave earlier, where we had one particular bottle of wine. You can have different users accessing it to see the characteristics of the bottle of wine, but only one of them can purchase it. You want to make sure that you have facilities for simultaneous access, such that if one person starts adding the bottle to a market basket or a cart and starts checking out, such that this only occurs for one customer and not for two customers, such that the same underlying bottle of wine is not being sold twice. So for that, we need appropriate facilities of concurrency control, especially, as I said before, when your databases are being opened up more and more in distributed environments. Data security issues are also very important. Some users may have read access, others may have write access, some may access the whole database, others may access only certain parts. This is very important as you work in distributed environments, right? So you want to make sure that all of that is appropriately managed, especially if you look at trends such as B2B, business to business, business to consumer, CRM. These are all going to stress the importance of data security. And the DBMS should also have facilities to appropriately manage data security. And the data security can again be managed in various ways. It can be managed via user accounts and passwords for users or user groups. All of that are again examples of metadata and actually integrity rules. The integrity rule can also specify what user or what user group has access to what types of information. So each user account will have its own authorization rules, which will be again stored in a catalog. So the DBMS also needs to foresee those facilities. It needs to have facilities for managing data security. Also, backup and recovery facilities are important. In case of loss of data due to a hardware or network error, or in case of bugs in system software application programs which may occur, you need to make sure that you have backup facilities. And you can have different types of backup facilities. You can have full backup facilities, which are each time going to fully back up the underlying data, or you can have incremental backups. Incremental backups, or the type of backups whereby you're only going to back up what has changed since the previous backup. It's not only about those backup facilities, but it's also about recovery facilities. So it also means that once you have a backup, you should be able to recover the backup and actually recover the state of the information system or the database, in this case, to the time before the event, the loss of data, the hardware or network error occurred. So you also have to actually have recovery facilities that allow you to do this in an efficient way. Finally, you also have performance utilities. Performance utilities will allow you to actually tune the database. It will allow you to actually tune the performance of the database. Make sure that you have databases which are very responsive, with good processing times, with good throughput times, and so on. Those performance utilities could also involve tools for buffer management, which are going to specify what is the content of the buffer. A buffer is a piece of memory in which you're going to keep information that is accessed a lot or information that was accessed recently. The DBMA will also have all kinds of index tuning facilities that will allow you to tune indexes, to define new indexes, to make sure you have appropriate access paths to the data. So those performance tuning facilities are facilities that will typically be adopted by DBAs to actually manage the performance of your database. This kind of concludes the first chapter. So remember, in this chapter, we first discussed some applications of database technology. We then defined the database. We then looked at the elements of a database system, and we concluded by discussing the advantages of using databases. Okay?